Computer. Okay, so I guess the first thing I'm going to talk about is from, you said practice exam 3 or practice exam 2?
Uh,
Second,
oh, wait, practice exam 3, part 2.
part 2. Okay, yeah. Oh, yeah. Okay,
Yeah.
so yeah, I have number 2 up, question number 10. Sorry, my brain just did a weird thing. All right, so we're gonna rank these in order of increasing rate of reaction with the hydroxide anion. So I'm going to draw them out first. So we've got A, which looks like this. This one has a bunch of methyl groups. Methyl, methyl, methyl. B looks like this. And let's not forget the electrons because those are important. This one has methyl, methyl, and then hydrogen, hydrogen. And then our C has all hydrogen. So we're reacting with a hydroxide anion, which is this, right? It's just a deprotonated water. So I'm going to draw one for each. And since both sides of the epoxide are the same, it doesn't really matter which side we attack. In this case, so we can go ahead and just, let's say we're attacking this side since it's closer. So we're going to attack this side of each of them. That is going to break the bonds. So the electrons are going to move back on to the oxygen. And then we just have to rank the order in which, which one is fastest to slowest. So we've got slowest to fastest. So hydrogen are very small, right? They're tiny, they're gonna move out of the way kind of easy, right? So if you imagine in C, there's not really an issue for that oxygen, that negatively charged oxygen, to get in there and attack that carbon. And that's what we mean by steric hindrance, right? Because when you have things like methyl groups, there's more electrons, because so when we just write methyl, we can't imagine it as well, but this is a carbon, and then we've got 3 hydrogens sticking out, right? So for each over here, we have got a carbon and then 3 hydrogen. That's kind of a lot for the oxygen to even navigate through. So C would end up moving, being the fastest reaction, because oxygen could be like, excuse me, hydrogen, I need to react with this carbon. Whereas A would be the slowest. And yeah, it has to do with steric hindrance, which is basically atoms, electrons, that kind of stuff, being in the way.
Okay. And I guess if I were to actually, if there anything on like this on the exam where we have to write it out, an explanation why this one's faster and this
Yeah.
one's slower, I guess I say that a steric hindrance would cause it to go slower because the, they're in the way. I got, or I don't know, that methyl groups are in the way. I don't know.
Um, I think you could probably just say A is going to go the slowest because it is more sterically hindered.
Oh, okay, and that's it.
Yeah.
Okay,
Yeah, I think it'll be assumed that you know what that means. So you don't have
okay,
to worry about explaining what you mean by sterically hindered. I just explained it just for the
yeah,
sake of explaining it. But on the test, I think you could just say it's sterically hindered, so it's going to go slower.
okay,
Yeah.
that's fine. So as long as you're concise, that's all that matters. Okay.
Yep.
I have more problems if Alea doesn't have any. I mean,
Alea, I'm sorry if I'm saying, I don't know if I'm saying your name correctly, but do you
Yeah,
have any questions?
Hi, sorry, I just sat back down.
That's okay.
Honestly, not really. This is like the first time I was able to actually be at an office hour, so I wanted to take advantage. Well, not really advantage, I guess, because I don't have any questions, but I just wanted to sit in and listen and ask questions if I was concerned about anything. So I'm just here to watch.
okay.
Okay.
I,
So
I
go
have a
ahead,
question.
ask me more.
Okay. In practice exam 2, there's another one that I thought was weird. Numbers. Practice exam 3, part 2, number 6.
Number 6.
So
Okay.
3, 2, 6. Yeah.
So we're synthesizing the target molecule, right? That's the right one?
Yeah.
Okay.
Yes. Yeah. And the chiral centers thing got me confused. So I was like, wait a second. How does? Yeah.
Yeah, let's take a look at this. All right, so we're starting with this, and we are ending with this. Yeah, so that does look intimidating. Let's break this down. So, I mean, we're not starting with much. So I'm not gonna even bother writing anything down on that side. But over here, I mean, we've got some stereochemistry happening, right? Something was added to this carbon and something was added to this carbon, and they're opposites. So that tells me like, okay, something was added anti. So we should kind of keep in mind all the different things that could add anti. And also an oxygen was added. So we must have had at some point a
MCPBA.
reagent, yeah, that added oxygen or like alcohol and then a hydrogen to the other side. Oh, that would be sin though.
Oh yeah.
Right,
But
because
wait, MCPBA plus H3O plus does anti-addition of OH, but it does it on both sides and only wants it on one. So I'm like,
right. So actually, I'm sorry, it looks anti, but it's actually a sin addition because what
oh,
was added on the same side. So it
right.
pushed the methyl group up. So we have like a hydrogen that was added, probably. Yes, definitely hydrogen, because um I'm gonna leave that for now and we'll come back to
Okay,
it.
okay,
But then we
okay.
also have an ether, right? That was added here somehow, or at least 3 more carbons. Yeah, this is a tricky one. I have a list of stuff here.
Okay,
These are at least new ones. I don't have the full list.
okay.
We could kind of take a look. And it might help us. All right. So, we might want to think about like retrosynthesis and like cutting the molecule, right? Probably
Can you
here.
add an epoxy?
Add an epoxide.
Yeah, to get the oxygen. Oxide adds on the same side across a double bond. So that'll push the hydrogen or the methyl, wait. Yeah, it'll push the methyl group forward
Mhm.
if the epoxide attached to the back, right? And then you could break that apart.
Oh, and the what you call it, the top part of the epoxide would be on the back side. Okay. Oh, because that is in it. Okay. That's
And
confusing.
Are you
Yeah.
thinking like this, like MCPBA?
Yeah, like that, except instead of being pushed forward, the oxygen would be pushed backwards, so it would be da 3 dash lines away with the O on the top. I don't know, instead of 2 black
Because it's just
triangles.
spin addition, right? That doesn't necessarily mean it has to be forward or backwards, right?
Yeah.
So
Right.
while that is a good idea, we're not really able to only end up with, so like if we followed up with like say an acid workup step, we'd have two
Right.
pages, right? But we don't. We had probably one. Do I have more of the things on here? I have, this is Courtney's list.
Okay.
So we can take a look. Oops. Let me make it bigger. 1 second. I mean, obviously on the exam, you're not going to be able to like go and look at
Yeah.
your list. But hopefully you're not going to be given one this. I definitely feel like this is on the
I
tricky
doubt
side.
it. But still, I
Uh,
guess.
yeah.
Well, because don't you need only like you need an acid to break that epoxide? It doesn't have to be H3O, it can just be another acid, right?
Yeah, but it would still add to both sides. Like if you break it, you're going to end up with a carbocation on the other side that then the acid would react with. So you would end up with
That's true.
an alcohol or methoxy or whatever it ends up being.
So it's
Okay.
tricky.
I do think it is safe to say that we had something with an OH here though, right?
Yeah.
So we probably had something with an OH. So what would we need to do? What would we need to add here to change it from an alcohol into an ethyl or ether? Sorry, ether. We added 3 carbons.
NaH. Yeah.
Yeah, yeah. So we would do the NaH, and we would
And
need
the
to add,
alcohol group with that. Yeah.
yeah, like that. Okay, so we have that. Now to take another step back from here, I do think it's important to remember, like, if we have the methyl facing up, then there must be a hydrogen facing down. So something was added, syn addition here. OH, and also anti-Markovnikov, right? Because this is on the left substituted. So we do actually have a reagent that does that. Yeah, here we go. Anti-Markovnikov and syn addition, right? It adds an OH to the least substituted carbon. That means it's adding a hydrogen to the other side, right?
Right.
So this was probably BH3THF and OH, H2O2. So that means that we had a double bond there.
Okay. And that's probably from a BR and just removing an and with say it's F, right? Right? Or like with NBS and light, just sticking it in
Yeah,
between where the
let's do that.
standard.
So we've got NBS and light. That's going to throw a bromine on here. And how do we end up with the double bond?
It would be Na plus minus OMe, right? So a non-bulky base, right?
Yes.
Yeah.
Yeah, I was hoping you weren't going to say bulky base because that would end up with
Yeah,
that, which we don't want
the
that.
thing, yeah.
Yep. Yeah. So there you go. It's a little bit tricky at the end there, but I think if you actually like pay attention to what you have and even like what's not written, like the hydrogen facing away is like implied. So taking note of that and like, oh, I have syn addition here. Something was added.
Okay.
Yeah. So hopefully that helps at least a little bit.
Yeah, it did. Yeah, okay, I know it, the BH3 THF does stick in OH and then an H on the opposite side, but I didn't think that, the chiral centers, that totally threw me for a loop. I was like, wait, what? So, yeah.
Yeah. It kind of goes back to, I guess, OChem 1?
Yeah.
So do you have another one? Or I see
Yeah,
other
I
people
do.
are coming in. Does anybody else
Unless
have?
if Courtney or
Yeah,
Molly, yeah.
Courtney's here. Charlie is here. Hello. Hello. Feel free to interject, ask questions. You can type them into the chat. Although when I'm looking down in writing, I'm not going to see them. So someone will probably tell me, Kristen, there's stuff in the chat you need to look. But yeah, next question.
If anyone else doesn't have any, I mean, yeah. All right. I have from practice exam part one, practice exam 3 part one, numbers 5 and number 12 as well.
All right, let's start with number 5.
It's another chiral centers type thing as well. So, yeah.
5. So this is the MCPBA? Yeah.
Yes, yeah.
So we've got this. And we're going to throw some MCPBA at it, and then we're going to follow up with an acid workup step. So we're protonating it. Actually, it says H2O HCl, but it's the same thing. They mean the same thing. So we have to pick which one we are actually going to get. I'm deciding if I want to actually draw them all out or if I just want to talk through it. I guess I'll draw them out and then we can do eliminations. Great. So we've got A. We've got B. We've got C. And we've got D.
Less.
Okay. So, we have a transalkene. And that
Use a spoon?
means that we will also have a product. Well, it doesn't matter actually because it's just a. So, sorry, I'm thinking of how to explain. Well, we have a transalkene, which means we're going to end up having a trans epoxide. So when the epoxide is actually like, let's do a two-step kind of thing here. So when we do add the epoxide, we have carbon, carbon. Our CH3 is going to be facing one way. Our hydrogen is going to be facing the other way. And then it's just going to be the opposite on the other side because it trans. So we're going to draw it like that. And then we need to get rid of the epoxide with our acid workup step. So in this case, we're going to have hydronium come in. This oxygen is going to go help itself to be protonated. Giving it partially a positive charge. And then that is going to cause another water to come in and attack this carbon or the other carbon. I mean, it's symmetrical, so it really doesn't matter which side you actually put it on. Because if you just turn it around, it's going to be the same thing anyway. So we would do that. And we would end up with this, and then water comes in here and deprotonates this and then gives us our finished product. So I guess if we are looking around at, oh yeah, okay, so let's look at A. Our H, or our hydrogen, and then our methyl and our methyl are like on the same side as each other. So like both the hydrogens are pointing up and both the methyl groups are pointing down. But because we started with a trans alkene, it cannot be this one because that would be cis alkene. So a cis alkene would give this. This would be the product for a cis alkene. And then same problem for D. And then with the plus minus, we actually have a it's a meso compound, right?
Oh,
So it's
okay.
actually not chiral because of that. So you can't actually form, so it's not going to be racemic. Right? So we've eliminated those two, but then we're down to, well, this says it's racemic and this one is not. So it would be C. And we can see here methyl is pointing away, methyl is pointing towards. So this ends up being the transalkene product. Does that make sense?
Yeah, it totally does. It completely cleared it up for me.
Okay,
Because
cool.
I guess because since I knew it was trans from the start, I wasn't 100% sure like after you made the epoxide where exactly it would be that there would be what's it called, CH3s would be in the triangle, I guess. So I was like, oh, duh, it's trans, one's away and one's towards. But yeah. I have another one though. I think it was number 12. Let me double check.
Oh, yeah, that's right. You did say another one. 12. Okay, let's do number 12. And anyone who is like just joining, this is from practice exam number 1. Just so you know. So here we need to give curved arrow pushing mechanism. So we're starting with this, the methoxy group. And we are acid catalyzing with H2O and heat. And we are told, oh my gosh, that is a huge plus sign.
Smells really good.
There we go. And we end with methanol. Okay. So when we have something that is acid catalyzed, how do we begin? What do we do first?
Protonate it.
Yeah. So what am I going to use
Yeah.
to protonate?
What's it called? OH3, yeah, or H3O, whatever.
Yep. You're correct. So that's going to have a positive. So the oxygen here is going to help itself to a hydrogen from our hydronium. That makes this a Lewis acid, Bronsted acid, and this is a Lewis base, Bronsted base. We're going to move on to the next step. So now our oxygen has a partially positive charge. And it's basically like, you know, see ya, I'm good. I'm a good leaving group now. So it ends up leaving with this positively charged tertiary carbocation. We also have water in our solution. So water is going to come in here and it's going to help itself and attack that carbocation. And that makes this our Lewis acid. And then this is our Bronsted, Lewis base, sorry, Lewis base. So now we have this here. Which we need to deprotonate before it leaves again. These electrons are going to move back on there. So this is our Lewis acid, Bronsted acid. This is our Lewis base, Bronsted base. And that is it, because that's how we end up here.
Okay, awesome. Because the thing I was confused about before, I was trying to use it like in the mechanism for the BRs or when there's excess BR or whatever. And, like I was trying to make it so, this would be similar to the BRs. It would get the one that's whatchamacallit, less bulky first, so it would get the methyl first. So, but it's not BR, it's water, so it won't be able to just yank the methyl group off of the oxygen, just like the BR. Yeah, and then get the other side after the fact. It's okay. Yeah.
Yeah, the BR, it's a little bit tricky. I think it's just because bromine is so electronegative that, you know, I guess if oxygen or bromine have like a tug of war with the methyl group, like the bromine wins, I guess, in that case. Yeah, but when you just have an oxygen, it basically, you're basically just cleaving that bond.
Okay.
Once you protonate it and prep it and it's able to leave, but yeah, it's gonna split there.
Okay.
With HBr, do you start with the do you protonate with the HBr or the hydronium? It's the HBr, right?
With the HBr,
Do you need a negative bromine?
Like if it's HBr catalyzed or just HBr by itself, it's
Yeah,
different.
it's this one. Yeah, with HBR. I believe it's with
So
HBR.
you still,
Or is it with hydrogen?
actually, I'm looking for an example.
Okay.
There was that one that we did the other day.
Yeah, you had it in your review. I just got done watching it, and you have HBR doing it. It's maybe it's a different problem.
Yeah, it's,
Concentrated HBR and heat.
yeah, I'm looking for a similar problem that I could just pull up. The question 8 from the practice test is it works a little bit differently, actually, which is interesting. This one in the practice test is a little bit more typical, I feel like, of how the problem how it usually works. The one I did in my review video yesterday was a little less typical, I feel like. Here, I'll do this one just so that you can see.
Okay.
So this is question number 8. There we go. So the mechanism for this one, well, we are starting with HBr, which is a strong acid. So we are going to start with protonating. I don't know, maybe it's because we don't just have like a small methyl group in this one. But in this case, the oxygen would grab that hydrogen. We're going to want to label our acids and bases. We end up with this. And in this case, our oxygen is going to separate, but it's going to leave in this direction. So it's going to keep that phenyl group.
So then the phenyl group part will be done, right?
Yep. So that's basically done over there. That's what we leave with. And then we have this. However, it's a secondary carbocation, and we could totally make that a more stable carbocation by doing a hydride shift. So we can actually shift this hydrogen and put it on a tertiary carbocation, which is exactly what we're going to do. And then we still have bromine floating around all by itself. And that is going to come in and attack that carbocation, and that makes it our Lewis base. And this is our Lewis acid, and then we're done. So I feel like that one proceeds a little bit more typically when we're talking about like acid reactions. I wish I could remember what number I did the other day so that I can like look at it again and see how it was actually different.
the bromine took a methyl group off of it.
Yeah, I remember, and I felt like that was a little different from how they usually, so I'm just I'm trying to find another example. You guys can ask me a question though if you'd rather I just answer more questions instead of looking this up.
I'll try looking for it really quickly, I guess, as well. It's one with a concentrated HBr and heat, right? So
Yeah,
I guess I,
HBR and heat.
there's number 5 in the mechanisms for ethers and epoxides. It's concentrated HBr and heat, and it's MEBr plus that.
Okay, let me take a look now. Number
I guess
5.
that would be the closest thing, or maybe number 7 as well. We got as another one, and 8.
Oh, okay, yeah. This is, I think number 5 is the one that I did.
Okay.
And then looking at number 7. All right, so let's talk about number 7 then, I guess. So this is number 7 from mechanisms involving ethers and epoxides. All right, so we're starting with an ether. And we are told that we are going to use excess concentrated HBr and heat, and that we are going to end with a bromine there and a bromine there plus H2O, right? So basically we know that we're going to be cleaving here and here, right? Because this is where we're adding our bromines. Right, a bromine is adding there and a bromine is adding there. So let's start with HBr. First step is always going to be protonating. So we're going to go ahead and protonate our oxygen. That makes this a Lewis acid, Bronsted acid, Lewis base, Bronsted base. And redraw. And since we are going to have a since they're both primary carbons, right? Because they only have that one bond there instead of two. SN2 is going to happen at both sites, right? So we've got primary, primary. So I think
I guess the least bulky one happens first, maybe. I don't know.
yeah, that's kind of what I was gonna go with. I was gonna go with the least bulky one happening first. So then this is going to separate. Then we're going to end up with bromine like that. And then we have this. And then we need to protonate that oxygen again, make it into a good leaving group. So we've got HBr. This is going to separate. And then bromine is going to come in again. Attack that carbon. This is going to leave. And essentially we end up with that. So both substitutions proceed via SN2, so they're rather quick. They're kind of fast. I'm gonna look back at the other one, number 5. So with number 5, we start with an SN2, but then we have SN1, SN1. And that's because we end up working with a secondary. So we are going to compare now. Let's do a comparison. So with question number 5, let's compare. So we start with this. Right, so here, this is actually a secondary. And then I guess you could consider the methyl group. I mean, that's going to happen that's going to happen SN2 because it's just by itself. It's basically a primary because it only has one, I mean, it's not even a primary. But yeah, I guess that's why it grabs the methyl group off so quickly. So we end with this. So we've got HBr. Our oxygen is going to protonate. That is always the first step, is that we do a protonation. This is our Lewis acid, Bronsted acid. This is our Lewis base, Bronsted base. So we end up with this has a hydrogen. You know, instead of just drawing a line, let's actually write CH3 here. This has a positive charge. So then SN2 is going to happen first, right? So that is why the bromine just comes in at this point and grabs that carbon or methyl group and these electrons, and basically the water and its big chunk of other stuff is going to leave. So that's our SN2 reaction, because we have this happening at the same time and this happening at the same time. So now we're left with that, and we have a secondary carbocation here. So in order to substitute the alcohol with the bromine, we need more than, we can't do it in a concerted fashion. We have to do like multiple steps. So we are going to have a carbocation rearrangement. So the first thing we're going to do is we're going to protonate and make water. So we have a good leaving group. So now we have water. Water is going to leave. We are going to have a carbocation. But I mean, you can even see from our product, like that's not, the bromine doesn't end up here, right? So we are going to have to do a shift. So this carbon over here has a phenyl group, it has a methyl group, but it also has a hydrogen. So we're going to go ahead and do our little hydrogen shift here, hydride shift, and move that carbocation. So it's here. Now our bromine is able to come in and attack that carbocation, and we end up with our final structure. So this all ends up being SN1 reaction. So I hope that cleared up a little bit, because I don't
No,
think
it
I talked
didn't.
yeah, I didn't talk about this that much yesterday. Actually, I don't remember learning this.
No.
So I'm like, oh, this is different. Fun. Sometimes they add to the curriculum and take other things away. So I think this was one of the switcheroos that they did. I don't remember this. But anyway, it's fine. We're
Okay.
getting together on this mechanism now. So that's fun. I like that though. SN2 and SN1.
Okay. At
Yeah.
least now we know for sure. Yeah.
Yeah. Yeah. So that's how that works. I mean, with you have an acid, you're always going to protonate first. But definitely take a look and see what kind of carbons you have. If you have you know, your primary carbons, which is going to end up being SN2, you're going to have a concerted reaction, versus if you have secondary carbons, you're going to have SN1, where you'll have a methyl shift or
Okay.
hydride shift,
Yeah.
maybe a methyl shift, but definitely a hydride shift.
Okay.
Yeah.
So just keep an eye on that. And I guess if it doesn't have any connections at all or whatever, well, if it's like a CH3 without any connections at all, it still goes through SN2.
Yep.
So,
Yeah.
okay.
Yeah, this was definitely concerted over here. So we had SN2 reaction.
Okay.
So the bromine grabbed the methyl and the oxygen left, and boom. Whereas here we had rearrangements.
I'm sure this is definitely going to show up on the exam. So, I mean,
Yeah,
it
I
helps.
think so. I think it was actually on her list of
Okay.
things that she might test you on for like mechanisms and stuff. So yeah.
So just keep an eye on that. Yeah.
Yep.
I have another one. It's the ether nomenclature problem number 6.
Okay, let me pull that up. Okay. So this is nomenclature. Okay, so for this, like the first step needs to be find the longest chain, right? So I guess comparing, you know, because we have to look on one side or the other side of that oxygen. So over here we have 1, 2, 3, 4, 5, 6 carbons, whereas here we only have 1, 2, 3, 4. So this is going to be like our main chain. So it happens to be a cyclohexene, because we have that double bond in there. So this is a cyclohexene. And
We wouldn't have to put cyclohex 1-ene because it's the first one, right? Or am I thinking of it wrong?
I think when it's on the first one, you don't have to do that.
Okay.
Yeah, I think it's just assumed that you're counting from that one. So like we would do 1, 2, 3, 4, and then having the 4 identified. So we'll do the center its chirality in a second. But we want to name the substituent. So we know it's going to be oxy because of that. It's an ether and it has some carbon attached. So I don't know if you guys remember, but when you have kind of like carbons shaped like this, we actually have a special name for it. It kind of looks like a T, right? So it's like T and then butyl. So whenever we talk about T-butyl, we're actually talking about carbons like without those connections. So
Kristen, can you go over
yes,
those names for that? Because I noticed tert, butyl, and there's a few other ones for butane, right? Or butyl groups, right? Or am I
yeah, there's
right?
butane, propane.
No, I know I meant like for like the arrangement of for butane specifically.
Oh, I don't actually have a list or anything.
Oh,
I think tert butyl is
okay.
probably the most common one. I don't know if there's other.
Because I know there's like ISO for a few of them as well, right? I know that's for propane, right? Or
Yes,
There's sec butyl too.
there is sec butyl.
yeah.
N-butyl, S-butyl, T-butyl, isobutyl. I don't think we've ever really used those.
I know it's all from OChem one, but like yeah.
Yeah, let me see. Okay, yeah. So just as I mean, do you want to just like know so you know, or because
I guess. Okay, it's fine.
okay, because I
Yeah.
don't know if I want to like add more stuff.
Yeah,
Just
go with my huge
yeah,
tangent. Yeah, it's okay. Yeah, it's fine.
okay. I don't know how useful it actually is right now.
Right.
But basically, this is a tert butyl, so
Okay.
it would just be a tert butoxy, T butoxy, because instead of the ill, we do oxy. So it's a T butoxy group. And then we also have to figure out the chirality at that point. So let me do another color. So this is going to be 1 because of the oxygen. Then this direction is going to be 2 because it's closer to that alkene. And then this direction would be 3. So if we start drawing that, it almost looks like an S. That's how I remember if it's an S or an R. So yeah, we're gonna have an S there. So then if we put it all together, it ends up just being 4S T butoxycyclohexene. Right? We didn't miss anything.
Okay.
Yeah, that's it.
And the T also has a dash next to it. Okay. Oh yeah. Duh,
Yep,
like
there's a dash there.
okay.
And I guess you could write T or tert, but I usually just write T.
Okay.
Yep. Any last questions before I finish up the session?
I have one last really quick one. It was yet again like another like explanation type thing. It was the cumulative problems for ether and epoxides, number 11.
Okay. Oops. I moved my papers over so I can open that. Number 11.
Yeah,
Okay.
it's like to give an explanation why the SP2 like thing won't work.
Explain why this reaction doesn't work.
Yeah.
So we have this. We have HBr and heat. And that is not going to create this. So the problem here is that all of these carbons on the benzene ring are sp2 hybridized. Sorry, I can't spell right now. But SN2 does not occur at sp2.
Okay.
So let's see if there's anything else. I would definitely say that's like the main reason. So if you need to give an explanation, I would definitely state that first, that SN2 or SN1 really is not going to occur at sp2 hybridized carbon atoms. And that's generally because the bond here is going to be too strong, right? So like the more S character you have, the tighter, like the shorter, the bond is actually a shorter bond because it's able to hold it closer to the nucleus of the atoms. So this bond ends up being like too strong to break. And then if we were to try to proceed SN1, that carbocation intermediate is not going to be very stable. I mean, generally we see electrons held pretty well, right? But like if you have like a positive charge on here, it just ends up being very awkward and it really just doesn't work well. So yeah, I guess just understanding those points and being able to explain it like that
Okay.
is what you would be looking for. Yeah.
Yeah, awesome.
Okay.
Yeah, thanks, Kristen, though,
You're
for
welcome.
everything.
You're
Totally.
welcome. All right. Good luck on the exam.